Our speakers today are Duchêne and Aline Parreau from the University of Lyon 1. And they're going to speak to us about taking and merging games as rewrite games.
Well, thank you. Thank you very much for this invitation. With Aline, we are very pleased to propose you this work, which is not a so recent work, but it was with Michel Rigaud and Victor Marceau. This is a work that we did when we were in Liège. And actually, this is going to be a talk about the correlation between combinatorial games and language theory and combinatorics on words. So it's not the first time that you are studying this correlation. Perhaps you have already heard about the talk of Robert about that. But in general, in the previous works, we were considering the combinatorics on works to encode the losing position or the winning position of a classical game. And this time it's going to be a bit different because we're going to play directly on the words. And we will use rewrite systems to define our games. And we will try to see how these games can model classical combinatorial games. So let's start. And as a first part, we will give you the material that we need for, maybe it's better like that. For our talk, so we will start at the first section to give you the material about combinatorial games that is needed to have a better understanding of this talk. So combinatorial games are defined in several books, but the most famous one is probably this one, which is a book of Balcombe, Conway, and Guy, Winning Ways. And in general, we consider that Conway was the first guy that really introduced and settled this theory. And to give you the constraints that we need to have a combinatorial games, we will give some. Here you have a picture of well-known games, and in combinatorial games, you need exactly two players. So for instance, if you consider a card game like the French Tarot, it does not belong to combinatorial games. And in the definition, you also require that there is no hidden information, that there is a total information for the two players, and also that there is no chance move. So for instance, the Ludo does not belong to combinatorial games. We also need that in the games that we consider in the strict definition, there is no draw, so there is always a winner. And there is also a finite number of turns. So with this condition, some other well-known games does not formally belong to CGT, so combinatorial game theory. And finally, we also define a convention for the winner. And in general, in combinatorial games, the winner is defined with the last move. And in the normal, I mean, the standard convention, the player who is doing the last move is the winner. So in other terms, the player who cannot play loses. So with these constraints, no one of these games that you can see on here belongs to combinatorial games. So what could be an example of combinatorial game? So there are others, of course, and perhaps I guess that you know the game of Nîmes and other games with heaps. So in general, such games with heaps of tokens are called taking and breaking games. So they are played with several heaps of tokens. So here I have an example with 3 heaps. So the heaps are depicted horizontally in our slides. So you have the 3 heaps of tokens, and the rules consist for each player. So the 2 players are playing alternately. And a move consists in choosing a heap and removing some tokens in a single heap with some constraints on the number of tokens you can remove, and also some constraints about the possibility to split the heap. And as we said previously, the player who cannot play loses. So for instance, if you are allowed to remove 2 tokens here from the heap number 2, you can take them and remove them, that's okay. But you can also take one token here in the middle of a heap. And in this case, you can split your heap into two sub-heaps. So for instance, here you have a heap of size 3 there and a heap of size 1 here. So it lands to this position. You can also consider choosing 2 tokens here, removing these 2 tokens, and then you will split into the heap 0 in 3 heaps of size 1. So this could be the rules of the so-called taking and breaking games. And among the family of taking and breaking games, there is a first well-known family that is called subtraction games. Actually, it only corresponds to the taking and breaking games where you are not allowed to split the heap. So you only remove tokens in a heap, but you cannot split them. And so to define such games, you only need a set S of integers that corresponds to the number of tokens that you can remove from your heap. So let's take this example where S is equal to 1, 2, 4. So it means that here in our example, we have 1 heap and you can remove 1, 2, or 4 tokens. So for instance, first player remove 1, second player can remove 4, first player can also remove 1, second player removes 4, and the first player can remove the last 4 tokens. And as we said that the player who is making the last move is the winner. In this case, the first player wins.
Okay, so what we were interested in, it will be to know who is the winner. And for that, and to define this, one very useful tool, at least in theory, is to construct the DAG, so the directed acyclic graph of the game. So really it's an example for the game subtraction 1 to 4. So how you construct this DAG? So you have one vertex for each position of the game. So here it's a game with 8 tokens. So for example, you start with 8 tokens and then you draw all the position you can go with one move. So for example, for the 8 token, you can take 4 tokens and then you go to the 4 vertex, and you cannot go to 7 or to 6, and so on. And since the game is finite and without cycle, you will have a DAG at the end. And now if you consider that you are playing to the game, it's equivalent to consider that you are playing on this DAG, and you have 1 token on the vertex at the initial position, and then you move your token, each player moves a token along an arc until you reach a sink. Okay, and then what we can do is that we can decide who is the winner starting from the end. So we can determine the winner, and here we assume that both players will play as the best possible. So if you are at sink and you know that you have a sink, then if it's your turn, you know that you are losing. So what we will say here is that the previous player is winning, and we write this position P. So the P stands for previous. And okay, when you have a P position, it means that previous player is winning, so you are losing. Actually, we also call them losing position. And then when you have a position with a label, you can look at the next one where all the successors are labeled. And here, actually, all the position where you can go to the P position, you know that you will win if you are the first player. So that's why here we put N. So N stands for next. So when you are in a position and you can move to a P position, then you are winning, because you can send your opponent in a position where you will be losing as a next player. Okay, so here it's the case for 1, 2, and 4, because in one move you can empty the heap, so you can go to the P position 0. And then you can just remove the vertices you are already labeled, and then you will find a new sink. And this sink, it means that he has no successor that are P positions. So you can label it with P, because if you have only successors that are N position, it means that in each case, your opponent will have a possibility to bring you in a P position. So this way, you can label all the vertices of the graph with N and P. And so what does it mean? It means that actually in any position, either the first player or the second player has a winning strategy, so as a way to win whatever is doing the opponent. So this is a very important theorem in a combinatorial game theory, is that one of the players has a winning strategy. So with the DAG, you know that one of the players has a winning strategy, but you don't know which player has, except if you do all this process. So actually, what we are looking, the problem we are looking in game theory is this problem. You give me a game position, give me a game, and I want to determine, is it the first or the second player who has a winning strategy? And so this is the first problem. And another problem that is related, but it's not the same thing, is, okay, you know that the first player is winning and you want to know how he's winning. So you want to have a winning strategy. So what does it mean is, for example, here in the vertex 5, you want to know that, okay, you have to play to 3. You want to give the move, the winning move. So it's two different problems. Sometimes you can solve the first one quite easily with a stealing argument and so on, but you cannot solve the second one. So it's related, but it's not the same problem. Okay, you can solve this problem with the DAG, but generally the DAG is very, very huge. So in subtraction game is still quite fine, but in general you have exponential size of the position set. What we can prove quite often is that they are in p-space. So I don't know if you all know p-space class, so I will just give you some idea about this class. So it stands, so actually it's an extension of NP. So NP, it was for problems where you can actually check if a solution is a good solution in polynomial time. And p-space is for the polynomial space. So actually, if you want to check that a position is a winning position, you don't have a good certificate, standard certificate. It's not possible in a polynomial time to check if a strategy is good. And you need actually polynomial space to do that. Okay, and so in this class, the standard problem actually are very close to games. And what is the standard problem for p-space class is this quantified Boolean formula problem. So in this problem, you have a formula, Boolean formula, that has quantifiers in the beginning. So it's for all and exist, and it could be alternating or not. And you want to know if this formula is true. Actually, if you think about what does it mean, it will be really like a strategy. What is a winning strategy? Actually, it's, okay, you have a move for the first player. For example, a winning strategy for the first player. It means that you have a move for the first player, such that for all moves of the second player, you have a move for the first player, and so on. And it's really exactly the same idea that in the quantified formula here. And actually, that makes this link at main formal. So you can transform this quantified Boolean formula into a game, which is called QBF game. So you remove the quantifier in the beginning, you just have the formula, and players, they take one variable, so in the order, and they choose a value, Boolean value for each variable. And at the end, the first player wants to make the variable, the formula true, and the other wants to make it false. Actually, first player will have a strategy if and only if quantified formula is satisfied. And this problem has been put to be even p-space complete, and is really a standard problem for the p-space class.
And so for many games, they belong to this class of p-space, and many of them are p-space complete. So computing the outcome, we mean the p or the n, is a p-space complete problem, and many reductions are done from this QBF game. But fortunately, there are some games that are proved to be polynomial when we are considering the computation of the outcome. And this is a case of subtraction games. So let's come back to the previous game that we presented to you, which is the game 1, 2, 4. So we have the DAG that Aline presented to you. And imagine we are considering the sequence of the outcomes, which is exactly the value p or n for each integer n. So you consider all the possible sizes for the heap, and you are looking if it is a p or n. And from that, you can note that this is quite regular because you have pnn, pnn, pnn for that game. And actually, we can show quite easily by induction that the position in this game is p, if and only if the number of tokens in the heap is a multiple of 3. And actually, this result is not isolated because we can prove, and it is well known, that for any finite subtraction game, then this sequence of the p and the n is ultimately periodic. So in other words, it means that if we know the period, then computing the outcome of the game can be done in polynomial time. So this is a nice result. But the only thing that remains open is the question of if we give to you the set S, which is the rules of the game, then computing the size of the pre-period and the period is an open problem. So we know that the period exists and the pre-period exists, and we have upper bounds on them, but computing it is not so obvious. But if you know this period, you can do some kind of pre-process and compute the period for any subtraction game. Then once you have the period, then solving it is polynomial. So that's why people in the literature decided to change a bit the rules and consider games where you can split the heaps, because when you don't split them in subtraction games, many things are known. And we give you a first example of a game where you can split the heaps, and it is called Cram. It's a game where each player can always remove 2 tokens. So the only move is removing 2 tokens in a heap, but you are allowed to split your heap into maximum 2 heaps. So let's get an example. So if we start with a single heap like that, and so the first player can choose these 2 tokens and remove them. And if you do that, you split your first heap into 2 sub-heaps, this one on the left and this one on the right. And the 2 tokens that have been deleted can be considered as the splitting between the 2 heaps. And so we can go on like that. So the second player can also split the left heap into 2 smaller heaps, and so on. People are going like that. So each time you can remove 2 tokens. So the 2 tokens must be consecutive. And like that. And if you are on this position, then you cannot move anymore because you have only heaps of size 1 that corresponds to the blue tokens. And so from a heap of size 1, you cannot remove 2 tokens. So you cannot play. So the player that made the last move is the winner in this example. And so this is Cram. But the problem with such a game where you can split the heaps is that the number of positions may be exponential when you do that, because you have many unions of heaps like that. And the question is how you can simplify the computation of the outcome when you are doing something like that. In particular, if you want to compute the DAG, the number of positions in the DAG for such games becomes very huge. So you need simplifications. And one interesting simplification is what is called the sum of games, or sum means a union of games. So you will clearly see what it is. Imagine you consider this first move from the first heap. So when you split into 2 sub-heaps, you go to a position with this heap of size x1 and this heap of size x2. So you have a sum or union of 2 heaps. And if you want to know the outcome of this union of 2 heaps, you are not forced to compute all the DAG for this position x1 plus x2. But maybe if you know the outcome of x1 and if you know the outcome of x2 as single heaps, maybe you are able to give the outcome of the union, the sum of x1 plus x2. And that's the idea. Is it easy to compute the outcome of a union of two heaps? So this is true for heap games, but this is also true for any combinatorial game in general. So imagine you are in a sum of 2 positions. The first one, you know that it is P, and the second one, X is winning either for the first or second player. So X, you don't know, maybe it is an N, maybe it is a P. Actually, you can prove that the position that is P is neutral, which means that you can remove it from the sum because it does not change the outcome. So the outcome of P plus X is the same as the outcome of X. Actually, to prove that, you just imagine that one player has a strategy on X. We don't know, maybe the first or the second player. And if you have a strategy on X, then you apply your strategy on X. And if your opponent is playing on this component, which is P, then you have an answer, and you will always have an answer because as it is a P position, it means that the second player has a winning strategy. And in other words, it also means that there is an even number of moves for the second player. So there will be an even number of moves for the second player here. So if you have a winning strategy on X, you apply it. And each time your opponent starts to play on P, then you answer. At the end, all the moves will be exhausted here, and you will go on with your strategy on X. So P plus something is nice. You just can remove the P. But what about position if imagine you have two heaps that are n positions? So n plus n, the union of two n positions, is it easy to deal with? Imagine you have two examples with the game Cram. So in Cram, this single heap is clearly n, it's winning for the first player, you remove the two tokens, it's over. The same for this one, but if you play on the union of the two, then the union is a P because the first player removes these two ones and the second player removes these two ones. So the second player is winning, it is P. But if you consider this sum, this is also something which is n plus n because this is n, and this is also an n position, the 4 tokens, because if you start, you just remove the 2 tokens in the middle and you win. So this is a sum of 2 n position, but if you play on the sum, then this time this is going to be n because the first player will remove the 2 on the left, and the second player will remove, for example, this one, and the first player will have the last move and will win the game. So when you are adding 2 positions that are n, it becomes open, and you will need a refinement of the structure of the n position.
Yeah, so actually, yeah, the 2 classes here are not enough to define the sum, to compute the sum. And it's why Conway introduced this Grundy value to be more precise, to refine the class of n position. So there are differences. So to define the Grundy value, you need the max, and the max is a function on a set of integer. And actually, you take the minimum non-negative integer that is not in the set. So for example, if you take this first set, 0, 1, 3, 5, the smallest integer not in the set is 2, a non-negative integer. If you don't have a 0, then it's necessarily 0, and for the empty set, it's also 0. And now, if you want to compute the Grundy value of a position, you take the max of all the position you can access to this position. And it is well defined because of the DAG. So if you want to compute, you can give an example on this, and you can compute it with the DAG, starting again with the n. And here you will see that the 0 position are exactly the P position. So the sink is necessarily a 0 position because you have no successor, so it's empty set, so it's a 0. And then, okay, you can just go to next vertex that has only one neighbor that is 0. So here it's 1. And its only successor has Grundy value 0, so its Grundy value is 1. And so on, you can go. So here you have Grundy value 2. And then you go to 3. And as before, since you don't have any P position, you don't have 0 Grundy value, so you will have 0 as Grundy value for 3. And so on. And you can, this way, compute all the Grundy value of all the vertices and so of all the position. And you have this thing that is not very difficult to prove, is that the Grundy value is 0 if and only if it's a P position. So this is quite important to remember for what follows. Grundy value 0 is P position, and then when it's positive, it's n position. Okay, and why we are happy with this function is, okay, we wanted to compute the sum, and actually you can compute the Grundy value of the sum if you just know the Grundy value of each component. And to compute this, you do the XOR operator. So this is not really important for that follow, but just for the curiosity. To compute this, you just write in binary your Grundy value, and then you do the XOR bitwise. And then you translate your binary sum into an integer. Okay, so this is very useful because now what does it mean? It means that you just need to know the Grundy value of one component, and if you are playing to a heap games, you just need the Grundy value to know the Grundy value for one heap, and then you can compute it for all the sum. Okay, so if I just put all the things I told you together, what important thing is that if you want to know if it's P or N now, you can just look at the Grundy value, and as I said before, the Grundy value of a position is 0 if and only if it's P. So what does it mean for the sum? It means that the sum is P if and only if you have the same Grundy value for x1 and x2. Because the XOR operator here, it's go to 0 only if the 2 values are equal. Okay, so now we have a characterization to compute the sum and to know the outcome of the sum. And so the only thing you need, it's to know the Grundy value when you are working on heaps, it's to know the Grundy value for one heap.
Yes, so that's why people are in general looking only at the Grundy values for one heap, and they are looking at the Grundy sequence. So this is the same as the outcome sequence that we showed you previously, but instead of the P and the N, this time we have the Grundy value. So this is a refinement of the outcome sequence. So if we come back to the example 1, 2, 4, so if you are computing the Grundy values, it's going to be 0, 1, 2, 0, 1, 2, 0, 1, 2, and so on. So the zeros corresponds, as Aline told you, to the P positions, and the 1 and the 2s corresponds to the N positions. So as you can see, you have also a nice structure for the Grundy values, because this is also regular. And actually, it has been proved that for subtraction games, it behaves nicely, because any finite subtraction game, whatever the set S you take, the Grundy sequence is always ultimately periodic. And what about taking and breaking games? So if we come back to the game Tram, so Tram, the game where you can split your heaps and you remove 2 consecutive tokens. And if we are computing the first values of the Grundy function for the first values of n, then you can see that it's more chaotic. You have 0, 0, 1, 1, 2, 0, 3, 1, 1. It's not so clear that you will have something which is periodic. But if you go further than 12, then it has been proved that actually the Grundy sequence for the game Tram is also periodic. But the period is 34, and there is a pre-period of size 53. And for all these games where you can split the heaps, actually there is a well-known family which is called octal game, and which tends to generalize subtraction games and also the game Tram, for example. And actually, octal game is a family of taking and breaking games where you can define all the rules that you want, but you can split in at most 2 heaps when you split. And to encode the rules of your game, actually, you are just giving some values, D1, D2, D3 to the rules. So this is the code for the rules of the game. And actually, D1 is the way, the value of D1 tells you the way you can remove 1 token. D2 tells you the way you can remove 2 tokens, and D3 the way you can remove 3 tokens, and so on. And each value, DI, is belongs 0 and 7, and roughly speaking, it tells you how you can remove your number of tokens, and it tells you if you can split into 2 subheaps, or if you cannot split but only remove your tokens on the extremity of the heap, or whether you can also remove your tokens but you must remove the entire heap. So you have these 3 possibilities. So you have many combinations, and actually you have 8 combinations for each value DI. So that corresponds to the name octal game, because the code is in octal. So if you give you an example, for example, the subtraction games 1, 2, 4 that we had previously. So the code, the octal code for this game is 3303. Because the first 3 tells you that you can remove 1 token, and 3 means that you can remove without splitting the heap. So this is the case in subtraction game. So you can remove 1 token for this game. You can also remove 2 tokens because your D2 is equal to 3. Then D3 is equal to 0, which means that you cannot remove 3 tokens. And D4 is equals to 3, which means that you can remove 4 tokens, but without splitting the heap. The other game Tram has also an octal code, and this is 07, which means that you cannot remove 1 token, but you can remove 2 tokens, and you can split the heap as you wish into maximum 2 subheaps. And another example that we did not tell you about, but 304 means that you can remove 1 token without splitting the heap, and 3 tokens by necessarily splitting the heap into 2 subheaps. So with these octal games, you model many different games. And there is a famous conjecture in CGT, in combinatorial game theory, a conjecture of Guy that asserts that if you take any finite octal game with this definition, then the Grundy sequence is always ultimately periodic. So it's not so obvious to look at them, and there are some games for which we know that the conjecture is true, but not so many. But for example, if you give the octal game 106, then it has been proved that the game, the conjecture is true, and that the game is ultimately periodic. But as you can see, the period is this very nice number, and the pre-period is also a very nice number. But this means that this game 106 is polynomial to solve. Another example, which is the James Bond game. So the James Bond game is the game 007. So actually, this is exactly the same game as the game Cram. But in Cram, you are allowed to remove 2 consecutive tokens. And in the James Bond game, you are allowed to remove 3 consecutive tokens. Sorry. And for this game, it's open. So people have computed the Grundy sequence up to the 2 to the power 28, but no period appears. Whereas in the game 07, which is Cram, the period exists. And finally, even for very simple games like this game 6. So this game is very, very simple. I mean, the 2 players have only one move, which consists in removing 1 token. So each time, each player removes 1 token from a heap. And the only constraint is that each time there is a heap of size 1, then you cannot play in it. So each time there is a heap of size 1, you can remove it from the game. So that's all. But each time you just remove 1 token, we don't know, it's open. The problem is open. We don't know if the sequence is periodic. And so there are some people that are actively working on such octal games. And in particular, there is Achim Flammenkamp, which tries to summarize all the results that are known on his webpage. And here you can see, so there are not all the octal games, but many of them. And as you can see here, so this is a period that is known. So for some of them, the period exists, and so which means that these games are polynomial. But for many of them, it's not known, and even the sequence has been computed until these very huge values, but no period appears. So the conjecture remains open, and even for many games, it remains open.
Okay, so this was a small introduction to combinatorial game theory in half an hour. And okay, so now you can come back if you were already knowing all these things, and we'll speak a bit more about words and combinatorics and words. So we'll speak about rewriting games. So what are these games? So it has been defined 20 years ago by Waldman. The idea is that you take a rewriting system that is terminal. So you take some rules on words, and then you play on a word, and players, what they do, they choose a rule and they apply it on their word. And when you cannot apply a rule anymore, then you lose. So let's just see an example here. So if you play on this word T, and with this 2 rule, AB, so you can remove a AB, or you can replace 3A by a B. So you start with this, and first player, you remove AB, then second player replace 3A by a B. First player remove another AB, and second player again, and then you are to BBA, where you cannot apply any rule, and so first player lose here in this game. You cannot play anymore. Okay, so this defines combinatorial game. It's fit well in the scope we give in the beginning. And actually, you can model, so it's quite simple games, but you can model a lot of games, and you can, for example, model all the octal games that we just defined before. So how you do this? So for example, for Cram, so you just take an alphabet with 2 letters. A will represent the tokens, and B will represent the separation between the heaps of tokens. So for example, this heap with 6 tokens, you will just take the word A6. Okay, if you have some tokens that have been taken and the heaps is split, and you just put a B in the middle. So what are the rules here? You can take 2 tokens. So this would be 2A, and you empty, you just remove the 2 tokens, but you don't put a separation. So it's just removing 2 tokens of a heap, but not splitting the heap. And if you want to split the heap, you use your second rule, which replaces 2A by a B, and then it splits. So it's this in this example, if I take the 2 tokens in the middle, then I will just replace them with a B and it makes the separation. I could also put 2B, but it's not necessary. So it's not difficult to see that it will be exactly the same game than cram. And you can do it so with the three rules that that Eric said. So in octal games, you have these three kind of things you can do. Either you can remove a certain number of tokens and you can delete the heap. So if it's for K tokens, then how you can delete a heap, it's just applying this rule. So B, A, K, B, you remove the A, and so you just delete the heap. You can remove some tokens without emptying. So here we can translate it with this rule. And if you want to split the heap into two non-empty heaps, you can do this rule. So with these three kinds of rule, and you do it for the number case, depending on your code, you can model all the octal games with this. So for cram, it's a bit simpler because we can do anything we want with the A, so we don't need to precise all this. Okay, so it's a nice setting to model a lot of combinatorial games. So the natural question after is how you can translate the Gay conjecture and the sequence of Grundy into words on rewriting games. So this is the work of Batman, actually. So now, instead of speaking of the Grundy sequence, what we will look at is the language that are made by the words with a certain given Grundy value. So it's what we will call LK. And LK, it's all the words that have Grundy value K. And the one class that will be very interesting us, it's L0, that is the losing position. So, okay, you can partition all your words into some classes like this, depending on the Grundy value. And what is very nice on actually the starting point of this talk on our work is this theorem is that, okay, if you have a sequence of an octal game that is ultimately periodic, then, and actually the reverse is true, if you look at the rewriting game, you know that you have a finite number of Grundy classes, not non-empty Grundy classes, and they are all rational. And so the reverse is true. So it's completely equivalent between the two. So this is very nice theorem making a link with this periodic sequence of Grundy and the rationality of the class. But it looks a bit magic, but so why is this true? So just in a few words, if you know that your sequence is ultimately periodic, what does it mean? It means that you can for one heap, actually, you are able to compute quite easily the Grundy value. And now you want to have, you want to prove that the Grundy class is for some K is rational. So you want to construct some automata for it. And what will look, you will note your words like this. So you can write any words in this way. And what does it mean? It means that you have n heaps, and the first one have size x1, second one have size x2, and so on. And you want to compute the Grundy value of this. So how it is computed, if you remember the theorem about the sum. So actually, when you put a B, it's exactly like doing the sum of the two games. So you just need to compute the XOR sum of G of x1 until J of xn. And you want to see if it's equals to K. And actually computing one component here, it's easy because you have only one heap. It's ultimately periodic, so you can do it with an automata that might have a lot of states. So you need the pre-period and the period, but then it's fine. You can compute this value quite easily. And then you can register the XOR operator before, because you know that you have a finite number of Grundy values. It's bounded, so you can remember more or less what is the Grundy value for all the sum until xi minus 1. And then when you have computed your Grundy value for the next one, with a product automata, you can compute the sum by adding one component and so on. And so at the end, you have computed your function here. Okay, and for the other direction, it's not really difficult. So you know now that all your language are rational, and you want to prove that the Grundy sequence of the octal game is periodic. So you want to go back to only one heap. So that's why you do the intersection with this language. That means that you have only one heap. And okay, you know that the intersection of the two languages is still rational. And since you have only one letter, more or less, because the B does not count here, you know that it will be a union of some language where you have an arithmetic periodic sequence here. And since you have in partition in total, you know that all your period will be multiple. And so at the end, you know that you have an ultimately periodic sequence here. Okay, so now if you have this theorem, if you want to translate the conjecture, it's just say that, okay, if you take a rewriting game, sorry, that model an octal game, the conjecture is that there is a finite number of non-empty Grundy classes and that each class is a rational language. So what we were wondering is that, okay, if you change a bit the rules, if you consider overwriting M, do you still have this rationality or not? What happens if you just change a bit the rules?
So the first case that we decided to consider, and that's what we did in our work, is to consider the case where in the rules we can delete the B's. So imagine, so you have your word with the B that are considered as separators between the heaps of A. And so if you have games where you can go from B to epsilon, which means that you can delete the B, and so you can merge heaps. It's like you can merge two consecutive heaps. And so we'll call such games taking and merging games. And so this is a formal definition. So it corresponds to games, rewriting games, where the rule set is given by this reductions. So consecutive A go to epsilon, or consecutive B are going to epsilon. And so as we have only reductions to epsilon, actually, to have a notation for such game, we only give the number of consecutive A and B that can be reduced. And so we have the same question as we had for octal rewriting games. So are the Grundy classes rational? This is the first question. Do we have a same result, or at least a conjecture for that for taking and merging games? And so we give a first example, which is A square B. So remember the rules. A square B mean that you can remove AA or B. So AA goes to epsilon and B goes to epsilon. And so to compute the Grundy sequence for this game, we are building the DAG, starting with the final position. So the two final positions are A and epsilon, because from epsilon you cannot move. So this is a 0, a P position. And from A, you can also not move. So this is also a 0 position. And so you are building the DAG. So from B, you can go to epsilon. And so the Grundy value is 1. This is N position. The same for A square. This is a 1 also, and so on. So you go on, you are building the DAG with the method that Aline explained you previously. And so you have something like that. So you have only 0 and 1s in your Grundy sequence. And actually, you can show, actually, just can note that with these two rules, that the quantity, the number of A and twice the number of B, actually, this quantity decreases by 2 after each move, only by definition of the rules. And so if you are looking at the final position, you can see that you have only the 0 and the 1 that corresponds to the P position for this quantity. So actually, since each time you remove 2, it means that the P position, so the Grundy values zeros, are only for the positions, so the words that satisfy the number of A plus twice the number of B's, modulo 4 equals to 0 and 1. So you have this property from that game. And so actually from that, you can show that for the game A square B, then there are only two classes of Grundy, L0 and L1, and each of them forms a rational language, because since you just want to compute this quantity modulo 4, you can easily, with such an automaton, do it. And so you have 4 states. Each value 0, 1, 2, 3 is the value of this quantity modulo 4. And so this 2, 1, 0.0 and 0.1 corresponds to Grundy value 0. And 1, 2, and 1, 3 corresponds to Grundy value 1. And so you can compute this quantity with this DFA. And so it means that you have a rational language. So this is nice, but unfortunately, not all taking and merging games are yielding rational languages. If you are considering, for example, this general game, which is a general taking and merging game, but you exclude the transitions A to epsilon and B to epsilon. So each time the exponents are at least 2. So if you consider any game like that, then you can show that the language L0, which is the language of the B position, is not a rational language. And to prove that, actually, you just consider the intersection of this language L0 with this rational language, this one. So actually, we just have to consider what are the p position of that game that are in this form. And you can show that the p position that are in this form are exactly these positions where the exponent I here is greater than the exponent j. So for instance, if j in the base case, if j is equal to 0, so you remove this term, and so you cannot move from that. So which means that this is a p position. And then in your induction, if you consider a position here, then actually this is a very easy position, because actually there is only one move that is forced, which is the concatenation of this b exponent L1 minus 1 with this b. So there is actually only one move which is forced for the first move, and then the second player will be forced to play the move with the a concatenated with this a k1 minus 1. So the first two moves are forced, and so from a starting position, the first two moves are forced, and you go back with your induction and prosthesis with the exponent I minus 1 and j minus 1, so you can apply your induction. So with that, you have this intersection with L0 with this language that is not rational because you are forced to count. And so L0 is not a rational language. But it's not so bad. It's not so bad. It's not rational, but we have been able to prove that in some cases, we have some languages that are context-free. In particular, if we consider the case where you have only one rule for A, so AK, and one rule for B, in that case, there are also two Grundy classes, L0 and L1, and the language for each one is context-free. From that, actually, to a short sketch of proof is that from any starting word U, actually we can show, since the rules are confluent, that there is a unique terminal word with such very simple rules. So there is a unique terminal word, and each time you consider a sequence of moves, which corresponds to a sequence of reductions, you can show that they all have the same length, and they all go to the same final word. So actually, since all the reductions have the same length, playing and deciding who is the winner only consists in deciding what is the parity of the number of reduction. If there is an even number of reduction, it means that there will be an even number of moves, and so the game will be losing, so G will be 0. And if there is an odd number of moves, then the first player will win. So we just need to count this parity of the number of reduction, and we can do it with a pushdown automaton quite simply. And just a note is that, so this is context-free, but if you do this, just if you have only one L equals to 1 or K equals to 1, you don't need to count in your pushdown automaton, because all the B's, for instance, can be removed directly. So you don't need to count each sequence of K or each sequence of L and use your stack. You can remove the stack and directly remove the B's, and so only a DFA is enough.
Okay, so this solves all the games with two rules. Okay, so then the next step was to go to case with three rules. And so here we restrict ourselves to games where you have the two rules, A give epsilon and B give epsilon, so that you know that you will go to the empty world actually. And so the first step is to add another A, and actually if you have rules with A, with an odd number of A, then it's easy, because you will remove, each time you will remove an odd number of letters, and you know that you will go to epsilon, so the parity of the size of the word will change each time. So actually the first player will win if and only if there is an odd number of letters in the word, starting word, and so it's very easy with an automata to check that. So next step is to put an even number of A, and the next one is A square, and actually the game A square B so is rational. You can compute the Grundy values of this game with an automata, but it's not simple and it's not trivial at all how it is done. So we compute with a computer, we found this automata for for word of small length, and then we try to understand the rules, and we finally found some invariants, but it's not simply. So you have to compute the number of blocks of size 3 you have in a sequence of A and B on the parity, and put all these things together, and then it gives why this automata is working. So it's a bit mysterious, but it's working. And so you have 4 Grundy values that are written in the states of the automata. And okay, this automata is computing the Grundy value of this game. So it was nice result. So then we were wondering, okay, we can generalize this game in 2 ways. Either you get A4 or you add A3. So actually, for the first one, we were not able to find any automata. So it seems that the Grundy value is bounded, but by 3. So it's not really large, but we didn't find any way. So we tried to compute the automata until I think size maybe 11 or 12 for the length of the word, but there is no structure that is emerging. So maybe if you want to study this game, what would be the first one to look at is it's this one. So it's not difficult, but it's changed. Okay, on the second one we try is A2 A square, A square and A to the 3B. And here we found an automata that is this one. And so it's working quite well in this, but the rule is again not so trivial. And so we add a A4, and here it's a new phenomenon that appears, is that it seems that the Grundy value is actually not bounded. So what is this sequence here? We compute, so you fix the size of the word, and you look at all the words of like 0, 1, 2, and you look at what is the maximum of the Grundy value. And you can see that it doesn't seem to stop and to grow. So our conjecture is that the value for this game is not bounded, but we try to find some words. We wanted to prove that it's not bounded and to find a sequence of words that hasn't bounded Grundy value, but this is not easy actually. This would be nice. So, okay, this is the first example of games where the Grundy value does not seem bounded. Actually, it's making a link with another question Wadman was asking. So another thing that Wadman proved is that if you take an octal game, so what we said before is that if you want to prove that it's periodic, one thing you can do is prove that all the languages are rational, and you have a finite number of non-empty language. So that means that the Grundy value is bounded and that they are all rational. And actually what is proved is that you have all the information in the L0 language. What does that mean is that if you know that the L0 is rational, then it implies that the Grundy value is bounded and that all the other languages are rational. So it seems very strong, but actually it's not so surprising. So why is it true? When you look at L0, actually it contains a lot of information, because you can do sum of games to compute the Grundy values. So for example, if you want to prove that 2 positions have the same Grundy value, what you can do is just to do the sum, and for that you just add the B between the 2 words, and then you have one word that is the sum of the position. You can try with your automata for L0 to know if it is P or not, and if it is P, if it is a P position, then you know that the Grundy value are the same. So actually in L0 you have a lot of information because you can do the sum of the game. One remark is that this is not true anymore if you look at the sequence. When you look at only one heap, it's not because the P positions are periodic that the whole sequence will be periodic. You have a lot of games for which there are only few P positions on one heap, and you don't know if the sequence is bounded or periodic or anything. So what is very important is that when you look at the language, you can really concatenate and modelize the sum of games. And actually, it doesn't also not seem true for taking on merging games. The reason is the same, is that when you cannot model the sum, because if you put a B and you concatenate your 2, and if you have a rule that removes the B, you don't have any more disjoint games. So the best would be to find a counterexample, and this could be a candidate. So for this game, it's not difficult to see that L0 is rational. So why is it true? Actually, if you look at the number of A minus the number of B modulo 3, this is a set of losing position if it's equals to 0, because when you go out of this, you have always a way to go back to a word where you have the same number of A and B modulo 3. But if you look at the Grundy value of these games, again, it seems not bounded. So this would be a good candidate for games where the P position are easy, but it doesn't seem to be a regular for the rest. But still, we cannot really answer to this question. Okay, and we are almost done. Just one thing we wanted to say is that we have also some undecipherable results. So if you take a writing game on one word, it's decidable to know if it's P or N, because you just have to compute the DAG and it's finite, so you can do it. But now if you want to have a bit more general results, and for example, if you want to have this result, so if you take a game and you take now a rational language of starting position, and you want to know if in your language there is a P position or not. So this is not decidable. What we also think, but we didn't prove, is that it's not decidable to determine if the P position are rational. So it was, we won't go into the details of this result, but it was some results of complexity. Okay.
And so to conclude, we have presented you this new bridge, which is not so new, but we found this bridge very interesting because there remains many things to do about this link between CGT and language theory. And but there, as you can see, there remains many things that are not understood. In particular, all the games with only 3 rules, and the smallest one is A for B. Grundy function is not so the Grundy values are seems to be bounded, but we have no idea about the DFA, if there is one. And in general, there is a lack of understanding between the construction of the DAG and the value of the rules of the reductions and the DFA. So we have found some DFA for some particular cases, but it's not so clear why it works for some of them. And when we just add a simple reduction, it doesn't work. So many things remains to be done on that. We can also consider the case where the rule A gives B is added. So it would correspond to taking and merging and breaking games. So probably it's going to be more harder. And also, so we have considered the link with taking and breaking games, but maybe these rewriting systems are also a good way to model other games that do not belong to this family. Well, thank you for your attention, and if you have any questions, we will be pleased to answer.
Oh, thank you very much, Eric and Aline. Does anyone have any questions? So when you're finding these automata for these games, is it just by brute force computer search?
Yeah, so generally it was the idea. It was this year we look at the games of small lengths and constructing the DAG with the quotient and trying to find some rules. And it's a bit strange, and something that was a bit frustrating is how it works. Why it seems we didn't find any link between the rules, the DAG, and the automata. And yeah, almost all the time we found something. There is a relation. It is really specific to this game, but we have no construction that is general.
But yes, this is brute force. To answer to your question, this is brute force for the first values.
Right. Does anyone else have a question? If not, thank you again very much.